So I am personally extremely happy to have Professor Antoniadis visiting with us. I am sure that all faculty are happy as me too, and of course he will give us a beautiful lecture. The abstract is available, so I only introduce him in the sense of professional development. Professor Antoniadis graduated from École Normale Supérieure in Paris, and soon afterwards, this is the French system, he was a member of CNRS, and then he got this position with École Polytechnique, okay, in Paris. And then
you're talking to the crowd.
Yeah. This is then he went to for a postdoc to SLAC in 83, this kind of time. So we met actually in 86 at the Institute of Theoretical Physics, now it's called KITP, Santa Barbara. It was in spring 86. So we know each other for a long time. And we worked on the things, different projects. But so right now he is at the University Sorbonne, emeritus, and then also Paris 6. But anyway, after SLAC, he came back, he went to CERN as a postdoctoral fellow, and then he went back to Paris, to École Polytechnique. And he was there until 2000 when he moved to CERN, where he stayed until he left, so to say. But when he was, since 2010, he was head of the Fiore division, which is in Europe called director. He was one of two directors, okay? Experimental physics and Fiore. So, yeah, he was the head of general physics. And the Fiore division did very well when he was a head. After leaving, he held different positions. He was at the Einstein Place, University of Bern in Switzerland, and then he went back to Paris, to Sorbonne, and the Paris 6, of course. And ever since, he has been visiting different places. I remember you told me that you are at Leuven, University of Leuven, and I was at the Louvain-la-Neuve, the French, in 84. Anyway, Lemaitre. Then, of course, you know, probably met him already in 2022. He was in Harvard, visiting Harvard University for 1 year.
For a semester.
No, it is 22 to 23. Okay, and now he's visiting at the Institute for Advanced Study, IAS, in Princeton, Albert Einstein Institute. And I think I finished on this thing, but he has everything going on for him. Okay? From what I heard is he's now Tidili Institute. He has got a contract with the Tidili Institute in Shanghai. This is where Frank Wilczek was the first director. Okay, so when Tidili was alive. So, very good. Welcome, Ignatios. You will explain to us all these great developments since the last time, extra dimensions, a cosmological constant.
Right.
Frank, let me do this. Yeah.
So thank you, Pavel, for the introduction, and thank you, department, for the invitation. The motivation starts from the following. Would like to, from the search to find the fundamental theory of nature, which is a challenge because we'd like this theory to describe both particle physics and cosmology. Particle physics is studied in accelerator experiments like CERN, which probes very short distances, so the structure of nature at very short distances, while cosmological observations probe the early evolution of the universe, at which scales the universe was very small and very hot, and therefore it was governed by the same physics that is the physics that we studied in accelerators. So the accelerator experiments and cosmological observations actually provide complementary information for the same underlying theory. So a few things about the theory. The microphysics is described by the standard model of particle physics, which provides very accurately description. And the last discovery was already 12 years ago with the discovery of the Higgs particle at CERN. On the other hand, the standard model of cosmology, which is under the name of lambda CDM, called dark matter and lambda for the cosmological constant, it's a phenomenological model that describes very well the observations, cosmological observations on the sky. So this is the temperature fluctuations, which is a picture. These are a picture study of the sky that correspond to a universe that was 1,000 times smaller than today. And the next, we have these two models, these two theories. If we compare the two, then we find the first strange fact that the content of the universe that we need in order to describe the observations is not the same with the content of the particle physics as we know the standard model. In particular, the ordinary matter, which is described by the standard model, is only a tiny fraction of the universe, less than 5%, while most of the remaining part is called dark. Dark matter, which is non-relativistic, it could be very well described by a new particle which is stable at the lifetime of the universe. But on the other hand, we have also what is called dark energy, which satisfies an equation of state, which is the pressure equal to minus density, negative pressure equal to minus density. And this could be very well be a cosmological constant in the Einstein equations, because if a cosmological constant is treated as together as a matter, then it satisfies exactly the same equation of state. The cosmological constant introduces two length scales. One is classical, because lambda has a length of -2. It's a classical scale. And this scale can be identified with the size of the observable universe. It can be inferred by the measurement of the Hubble parameter. And it's about 10 to the 26 meters. And another scale is a quantum scale when we want to interpret the cosmological constant as an energy density. Then we have to divide by the Newton's constant and then use C and H bar in order to have a length scale. And this length scale is very different from this one. It's 85 micrometers. So this curiously is very near the distances where gravity is probed is checked at the laboratory experiments, and particularly Newton's law. And right now it is probed up to distances of 30 microns, so which confirms that Newton's law is valid up to that distances. So my title has extra dimensions. So extra dimensions is important ingredients of theories of quantum gravity, such as string theory, which precisely is a candidate. I don't know, it doesn't go to of a theory that can describe both particle physics and cosmology, because it contains quantum gravity. Now, what are the extra dimensions? Take a parenthesis. Were introduced in the beginning of 20th century by Kaluza and Klein, trying to essentially unify electromagnetism with gravitational interaction through hard dimension, through an extra dimension. The first question in extra dimensions is if they exist, how they escape observations. And the possible answer is when they have finite size. So it means it costs energy to send a signal. Or if you want finite size, one can think about, let's say, an extra dimension which has a size which is a small cycle. So if we are far, we don't see it, but as we approach, then we see the structure, we see the extra dimension. You could have two extra dimensions with a different topology or geometry, like a torus. Similarly, if one dimension of the torus is bigger than the other, as we approach, we'll see first a cycle, then we will see an extra one. So when I say see, it's precisely through energy, like accelerator experiments, higher energies probe smaller distances. So the smaller energy to probe the extra dimension is what is called the compactification scale, is the inverse of the size. And that's how we can impose experimental limits without much thought. In other words, what is the smallest size that it's probed by accelerators? A few TeV, which corresponds to a size less than 10 to the minus 17 centimeters. So the next question is how they could detect their existence, what we will see when we have enough energy to probe an extra dimension. And the answer was given again back by Kaluza and Klein, where they observed that the motion of a particle in the internal state, in the internal space, gives rise, from our point of view, and to a mass spectrum. So consider, for instance, one extra dimension, a circular dimension, on a circle of radius r, and suppose that we start with a light that's massless in higher dimensions. Then the plane waves have an extra component. So y is the extra dimension, and p is the corresponding momentum. Since the extra dimension is periodic, the momenta in the p in the internal momenta are quantized in units of the inverse radius. And then this reproduces what is called the tower of Kaluza-Klein particles, with masses linearly increasing with the inverse radius. So n equals 0 corresponds to the ordinary to the photon 4 dimensions that we see, but then you have other massive particles that correspond like massive photons with the same quantum numbers as the photon, but with a mass. And therefore, as we increase the energies, then we will emit massive photons, and this will be the way to detect it. And if the energy becomes sufficiently large, then one can observe a quasi-continuum of particles, and this is what reproduces the propagation in the internal dimension, the internal space. On the other hand, there can be that if the extra dimension is very large, as I mentioned before, the bound that we find is 10 to the minus 17 centimeters. This this has an assumption that we can send signal, electromagnetic signal, for instance, in the extra dimension, that the photon propagates in the extra dimension. However, it may be that our universe forms a sort of membrane which is localized in the extra dimension and which communicates with it only by gravity. So, in other words, there are two types of extra dimensions. One type is along the membrane, the brain universe, in which case their size is constrained to be very small, 10 to the minus 17 centimeters. But there could be also extra dimensions along perpendicular to our universe, which communicate with us only gravitationally, and then in that case the only bound that we have is from the Newton's law, which is the 30 microns, and in that case these dimensions, which I call transverse to the brain, can be much larger than the others. So that was very important, and it was studied in the past as a possibility to explain the hierarchy, the particle physics by the hierarchy by a low-scale gravity. In other words, a gravity that becomes stronger at much lower energies than the Planck scale. There is a way to understand this, that there are extra dimensions in which gravity only propagate. Then the total force of gravity is the observed force times the volume of the extra space, of the compactified space. And this means that the fundamental length, the fundamental scale, m star, so which corresponds to the higher dimensional Planck scale, can be will be smaller than the Planck scale, exactly by taking into account the volume of the extra dimensions. So the volume of the extra dimensions is given by the ratio of the known Planck scale over the higher dimensional scale. So this was an idea in the past that at that time that we could imagine that the fundamental scale where gravity becomes strong could be near the TV energies, and all interactions could be unified at that scale. Of course, experimentally we don't have any signal, or actually we don't have a signal of any physics beyond the standard model up to now. On the other hand, there was an extra motivation over the years that came through the so-called swampland program, introduced by WAFA in 2005, which essentially is a program in which we try to find the constraints on the effective field theories that can be consistently extrapolated into ultraviolet by coupling them to gravity. And the one particular conjecture which is relevant for this case is what is called the distance conjecture, which says that if we look at large distances in the field space, then by large means large compared to the Planck length, then there is an exponentially a tower of exponentially light states with masses which are exponentially small with a distance, with an exponent which is order 1 in Planck units. There are two generic possibilities in order to have these large distances. One is to have a decompactification of an extra dimension, and then this the tower of states is just a Kaluza-Klein states, which I mentioned, they grow linearly with the compactification scale with the inverse radius. However, in that case, the distance is the logarithm of the radius, and therefore they obey this.
R2 minus R2.
Yes. Another possibility is to have a tower of string excitations. In that case, this mass is the string scale. So this immediately points on a possibility that the smallness of some physical scales in natural could be a manifestation that we live at a large distance corner of the landscape of all possible vacua, for instance, within string theory, where the natural region is the region where all the scales are of the order 1 in Planck units, but since we know that some of them are very small compared to the Planck scale, this could point out this possibility. So this idea was applied to the dark energy. It was based on the observation that when you have when you look at vacua with a cosmological constant, actually negative cosmological constant, then it was argued that the distance is the logarithm of the cosmological constant, and assuming that this is also true for positive cosmological constant, then one can apply it for the dark energy, and one can immediately obtain as a result, as a consequence, that there should be a tower of states with a mass which is proportional to a power of the cosmological constant. When I say power, it's always in Planck units.
Around 0.7 millielectronvolts.
Yes, so using theoretical and experimental constraints, you can find that you can fix A to be 1/4, this power to be 1/4, and then you find that this scale is near the micron size. So that was the motivation that somehow brings these things together. Now what I will make it now another parenthesis by asking a different question, by looking at the large hierarchies in particle physics and cosmology. So in particle physics, one of the largest hierarchies, if you compare gravitational interaction to the other forces of nature, then one can ask the question why gravity is so small, so weak compared to the other interactions. This amounts to point to the ratio between the Planck scale and the electroweak scale, the mass of the W bosons and Z bosons were discovered at CERN. Why they are so light, W and Z boson, compared to the Planck scale by 16 orders of magnitude. A similar question can ask in the universe, in cosmology, why the universe is so large compared to our causal horizon. In other words, when we extrapolate back in the past, using the present expansion of the universe, then we find that the universe, we obtain a universe which is much smaller from what we observe. In other words, we have most of the universe is not causally connected with us, and we need at least 10 to the 15 factor bigger in order to explain to explain why all the sites that we observe in the sky are causally connected with us. Of course, you can say why they should be causally connected. One of the reasons is that we observe that the universe is at large distances is homogeneous, is isotropic. So if there is no reason for this if most of it was causally disconnected by us. A possible connection, so what I will discuss is a possible connection between these two hierarchies through the extra dimensions, through the large extra dimensions. Their existence is required in string theory, and we know that I mentioned before that extra dimensions could explain the hierarchy, this hierarchy here, by observing that if there are large extra dimensions, then the real force of gravity is much smaller than the fundamental Planck scale. On the other hand, we know that a way to address the causality, the horizon problem, as it is called, is by introducing a period of fast expansion, like exponential expansion, or inflation as it is called, which is a period in which the universe is expanded with a speed faster than light. And therefore a small fraction can be causally connected after some period of expansion, or of large expansion. So the idea is that a way to connect these two hierarchies is through extra dimensions, by assuming that the extra dimensions could obtain large size by a higher dimension inflation. In other words, initially the extra dimensions could have small size, the size of the order of the fundamental length, but then there is a higher dimension inflation that inflates both the extra dimensions and our universe in a uniform way. And as the extra dimensions expand, then the four-dimensional Planck scale changes, becomes bigger, and at some point it will require, it will acquire the size which is required to explain the present strength of gravity. So an example is to start to discuss an extra dimension, what is called a dark dimension, which has a micron size, as I mentioned before. And an extra dimension of a micron size implies that the gravity becomes strong at energies which are 10 to the 19 GeV, 10 to the 9 GeV. So means distance which is 10 to the minus 22 centimeters. So if one can start at this fundamental length with an extra dimension of the same size, of the same order of magnitude, 10 to the minus 2 centimeters, and blow it up with inflation to the micron, which is precisely the size which is required so that the four-dimensional gravity acquires the right value to explain why gravity is weak. This blow up requires 40 EFOLs to go from this scale to the micron size. So the five-dimensional metric has a scale factor which blows up, is the same scale factor for this our space, non-compact space, 3 space, and for the extra dimension, which starts with some initial value of the radius, which is this one. And the scale factor expands exponentially with the time, with the proper time, 5-dimensional proper time. After the end of inflation, one has to go to the dimension becomes large, and one has to go to the 4-dimensional proper time, so one has to rescale the metric so that we go to the Einstein frame, which fixes the 4-dimensional Planck mass. And this rescaling implies that in four-dimensional proper time, the scale factor expands faster than the 5-dimensional one, So if you want in four-dimensional proper time, the radius expands as t squared, while the scale factor of our universe expands as t cubed. So 40 e-folds for the radius means 60 e-folds for our space, and this solves the horizon problem.
This relation is only valid for one extra dimension.
Yes.
What happens when you have two extra?
Yeah.
You have different powers.
You have different powers.
Yeah.
This is the extra thing, which always works.
Yes.
So it's true, there are different powers. However, the scale of gravity becomes smaller. The scale of where gravity becomes strong becomes smaller. Of course, it cannot become smaller than 10 TeV, which is the experimental bound. But since the fundamental scale becomes smaller, means that the inflation scale becomes smaller, and therefore you need a smaller number of e-folds in order to solve the horizon. And if you put this information together with experimental bounds, you see that always it works. So it's an observation that it could be done. It could have been done in the past. I don't know. It was not observed before. But this, I think, it's a nice observation because it allows to connect two big hierarchies, one from particle physics and another from cosmology, through the same mechanism, which is higher dimension inflation. So the next question is, if we have higher dimensional inflation, then what happens with the density perturbations, the temperature perturbations that are measured at the CMB? Can higher dimensional inflation be compatible with the observations? So for that, I put back this experimental result, which compares the temperature fluctuations, so these are the various points, experimental points, with lambda CDM using, let's say, four-dimensional inflation. And one sees that this agreement is at small angular scales. So if we look for angles which are in the sky, which are bigger than approximately 10 degrees, then there are errors, and one cannot see exactly what happens. Actually, four-dimensional inflation would imply that this scaling varies. It's a line here.
So the green solid curve is a theory of prediction?
It's measurement.
No, these are the measurements. Okay, so
all the points are measurements.
Yeah, the green,
green solid line.
the green is just the lambda CDM. So this large scale should be constant. Okay, there is a bit distortion. I mean, normally it's constant everywhere, but these curves come from the propagation of the density perturbations when they come back. When they enter our horizon and they propagate up to observations. So at very large distance, this propagation becomes less and less important, and it goes to constant. But of course, one doesn't have data at this region. So the main message from here is that if a theory predicts deviations, these deviations should appear at large scales, larger than 10 degrees. And there were already some preliminary indication that maybe there is violation already of scale invariance.
There is such a thing as intermediate asymptotics. So this is always in some range of momenta, from k minus at minimum to maximum.
So as I just mentioned in words, the main prediction of inflation as exponential inflation is that is the one of scale invariance. And this comes from the fact that the inflaton, which is a scalar field that has some potential which is quite flat at some region where you have inflation, it behaves as a massless scalar in the zeta space. And its fluctuations are scale invariant, which means that in momentum space, the fluctuations of the inflaton, which are the fluctuations of the density in some particular gates, behave like 1 over k cube. Now, in right, yeah. Of course, we know that it's not now 1 over k cube. There is some small deviation, but this is irrelevant for this argument. So this first approximation is scale invariant. Now, if you have 5-dimensional inflation, then you would obtain again scale invariance, but the 2-point function would be like 1 over k to the 4, because the power is the dimension of the space. And now this k to the 4, in which I put a hat, contains the 3 momenta that we know, the 3 space momenta, plus the excitations, which are the Kaluza-Klein excitations, so along the extra dimension. So if we were live in 5 dimensions and we could measure the fluctuations and the momenta in 5 dimensions, then we would have again scale invariance as we have in 4. However, as I said, we don't live, we cannot live in 5 dimensions. We live on a brane, which is because if you have an extra dimension at the micron size, you cannot send the standard model should live on a brane, otherwise it would be incompatible with accelerators, with accelerator experiments. Which means that this brane is localized in the extra dimension. Actually, we don't observe these excitations, and therefore has to sum over all of them, since the brane is localized. I mean, the Fourier transform at the space equals 0, at y equals 0, corresponds to a summation over all n, over all momenta in the extra dimension, which means that the 2-point function becomes more complicated, and it has two different behaviors. On this, k is a comoving momentum, so it's the inverse of the comoving length, and r is the extra dimension, the size of the extra dimension. So if we look at large momenta, so it means small wavelengths, small angles, then one finds scale invariance. I mean, this summation over the excitations had to be done and reproduce a scale invariance as we know in 4 dimensions. On the other hand, if we look at large distances, large wavelengths, which means small momenta, then the scale invariance is violated. One finds an amplitude which goes like 1 over k. K is the 3 momentum, which means that the spectral index changes, becomes from 1 becomes 0. So in that case, that limit is dominated by a 4-dimensional power law inflation of t cube. But in the other limit is dominated by the full de Sitter space, I mean 5-dimensional de Sitter space. So the question now is if we look at want to extrapolate this 10 degrees in the sky in the past up to the end of inflation, and we should find the micron scale. So this extrapolation, first of all, up to MEV, which is temperatures of MEV, which are the nucleosynthesis scale, can be done easily. One finds that the megaparsec, which is the 10 degrees in the sky, it's gigaparsec today, is megaparsec at the time that the universe was 1,000 smaller. So as it is observed by CMB observations. Then it becomes 10 to the 15 meters, means 1 billion kilometers. Now, if we want to go back, one has to multiply by this MEV over the temperature. Let's say I have to go up to the reheating temperature, and then in the period between the reheating temperature and the scale of inflation, the end of inflation, one can add any period of evolution in which the inflaton, let's say, oscillates, for instance, which corresponds to a pressureless fluid with W equals 0. Then one finds that indeed one can go to the micron scale, as long as the reheating temperature is bigger than MEV and the scale of inflation is bigger than TV. So this is indeed possible. So if we go now here, we know that the limit at small angles reproduces the 4-dimensional result. So we can make the matching of this limit with what we observe. And then at larger angles, it deviates like 1 over k. And then and this is the part of the deviation. So this curve would be the 4-dimensional prediction, which is flat, scale invariant, while this is the 1 over k that gives more power. And of course, one cannot make any conclusion with the present errors. But in the future, okay, here I was quite conservative. I used multiple moments less than 10. Normally it's up to 30, I think around 10 degrees. The point is that in the future it may be that the errors are reduced at this region, and then one can perhaps see a deviation. Actually, now this computation of scale invariance can be corrected by the slow roll parameters, because the potential is not flat; it's a little has deviations from the flatness, and these deviations are characterized by the slow roll parameters. And one can obtain the deviations. So what you see blue here are the deviations from the 4-dimensional result, and these deviations come from the extra from the graviton in 5 dimensions, which has extra degrees of freedom, has 5 degrees of freedom. So in addition to the tensors, it has a scalar, which is the radian, and it has also vectors. So all these blue are corrections that come from the 5-dimensional graviton, and these corrections are suppressed by a slow roll parameter. So right now there is no precision, but in the future, when the precision even in the scalar perturbations becomes improved, then one can basically compare and see deviations. Another place where we can see deviations is in the so-called bispectrum, which is the 3-point function. You look at you compare not to fluctuations of 2 points in the sky, but 3 points. In that case, when you look at at small angles, where you obtain in the region where the scale invariance is restored, you obtain a function which depends on the angles of the shape. So there are 3 points, so there are 2 parameters there. So K1, K2, K3. And so there is a scale invariant result, and therefore there are two parameters which define the shape. So I can do this computation in 5-dimensional gravity in the scale invariant region, and one can compare with a 4-dimensional one, and one finds different shape. So this is a way, of course, to discriminate between the two when non-Gaussianities would be measured at some point. The reason that the shape is different is because in 4 dimensions, but also in 5 dimensions, although scale invariance is restored, the conformal invariance is broken by the slow roll of parameters, and therefore that's why the shape is not predicted. Here I mention all the results that we had with Pavel and Emil Motola, in which we required a conformal symmetry, and in that case the shape is still different. So in principle, if non-Gaussianities are measured, it's not just one parameter like the spectral index in the 2-point function that can be fit in many ways. But here you have but here you have but you have a whole function of 2 parameters. So in principle, here you can make a distinction between the various proposals.
But I mean in the position space.
Yes, the position space. Yeah.
The amplitudes of 2-point function, 3-point function, and universal index.
Yeah.
The conformal dimension is the same for 2 and for 3. Yeah.
So before I finish, I would like to discuss a couple more physics applications of the dark dimension, and another was dimension which has a micron size. So this is a review that you can, if you want to look at it. One has to do with neutrino masses. If one has extra dimensions of the micron size or sub-millimeter size, then in principle one can ask the question how these theories we can explain the smallness of the neutrino masses. It was observed already 20 years ago when these extra dimensions were introduced, that a natural explanation of small neutrino masses is if the right-hand neutrino can propagate in the extra dimension the same way as the graviton. Then the smallness of the neutrino masses comes from the suppression of the wave function, in the same way that the gravity becomes weak when there are extra dimensions. In the same way, the wave function suppresses the interactions of the right neutrino to the brane and its masses. And indeed, when you do, since that time, there have been several times analysis of neutrino oscillation data with 3 bulk neutrinos, and this is the present bound of on the size of the extra dimension. So it's comparable. It's actually better than the Newton's law. But on the other hand, this analysis assumes that these right-hand neutrinos have no masses, bulk masses, have no high-dimensional masses. If you put high-dimensional masses, then this bound can be relaxed. And in principle, it can go up to the bounds from the Newton's law. Also, another application of extra dimensions, if the neutrino propagates, the right neutrino is a 5-dimensional state, is that the neutrino masses should be Dirac type and not Majorana type. And this is, of course, an extra prediction. The last thing I want to talk is about new dark matter candidates that this proposal brings. Actually, there are 2 possibilities. One is that the dark matter is primordial black holes, but 5-dimensional primordial black holes. In other words, black holes for which their size is smaller than the micron size, than the size of the extra dimension. Then these black holes behave like 5 dimensions. And in that case, The 5-dimensional black holes live longer than the 4-dimensional ones with the same mass. So this is this for 4 dimensions primordial black holes. The exclusion plot, limit on their. So this is the mass of the black holes, either in grams or in the solar masses, and this is a fraction of primordial black holes to be dark matter. So if one wants, let's say, to explain 100% the dark matter, you have to look just here on the top. So in 4-dimensional black holes, there is a small window between 10 to the 17 and the 21 grams, for which the primordial black holes can be dark matter. However, if you go to 5-dimensional black holes, since they live longer, these bounds on the lower mass that come from evaporation go away, and you can extend the mass range by approximately 3 orders of magnitude.
You want to have all dark matter coming from this
Yeah,
rise in this
yeah,
direction.
right, yeah.
Okay.
Now, of course, if you go to if the black holes, if you go to 6 dimensions, then they can live in, you can have even smaller masses.
Yeah.
The other possibility that was proposed by a group of WAFA is that the dark matter could be composed by excitations of Kaluza-Klein excitations of a graviton, the graviton which goes to 5 dimensions, and these excitations have internal decays. In other words, a heavier excitation can go to a lower one, so there is parameter there to parameterize the decay. Adjusting this parameter, one can realize a phenomenological proposal which was called under the name of dynamical dark matter, in which the mass of the dark matter changes with the time, with the temperature. Here, starting from MeV at matter radiation quality, and going up to 50 keV today. So this just to tell you that okay, there are also these new possibilities with the extra dimensions to the dark matter. And finally, I would like to conclude with one extra question that may ask: why one extra dimension, let's say, or 2? You cannot have more than 2, because then the dimension should have micron size, because it's connected to the dark energy. And if you have more than 2 of micron size, then the fundamental scale of gravity is very small, smaller than 10 TeV, much smaller, and it's excluded. So in the case 1, there is a possibility that it was proposed that this difference between one dimension and the others can be explained within the M theory, which has 2 10-dimensional boundaries and an extra dimension here. So this dimension could be the size of the extra dimension. And if you put the numbers, you find that the M theory scale, the 11-dimensional gravity scale, is 10 to the 9 GeV, and the extra dimensions are the micron, and then all the rest, the volume is of the same order as the 11-dimensional scale. So I would like to conclude. So the 2 messages is the first is that what I mentioned is that the smallest of some physical parameters might be a signal that we live at a large distance corner in the string landscape of vacuum. Large distance means, in practice, large extra dimensions and low scale gravity. Now, how low, it depends on how many you have. If here is 1, then the gravity is 10 to the 9 GeV. If it is 2, then it's 10 TeV. This framework provides interesting phenomenology. I mentioned the neutrino masses, dark matter, cosmology, and so on. And the other message is that large extra dimensions could arrive from high dimensional inflation by connecting the weakness of gravity to the size of the observable universe. And this gives a new possibility for generating density fluctuations from 5 or 6 dimensional inflation. Thank you.
I suggest that now we have time to ask questions, of course. If you have questions, please ask. Yes.
A few slides ago, you had right-handed neutrinos.
Yes.
Could they not be the dark matter without the necessity for extra dimensions?
No, they are too light, the neutrinos.
Pardon?
Yeah, they are too light to be
Well, they
called
could
dark
be.
matter. I mean, it could be a fraction, maybe, or a warm dark matter, but
But they have been, they could be MEV or KEV.
yeah, no. Here sorry. I mean, the neutrino masses are of the order of milli-electron volt, right? Now, of course, the bulk, the right-hand neutrino could be much heavier.
Yes.
In that limit, indeed, the neutrino mass, the lowest mode, the zero mode, which pairs with the left-hand neutrinos, becomes very, very light. And indeed, that is a possibility that could be studied, but yeah. Actually, for neutrinos, there is an independent way to probe extra dimensions by experiments of the type like Catherine, which look at the endpoint of the spectrum. They look for sterile neutrinos, but Kaluza-Klein excitations behave similarly. So they are in the same way that you produce the Kaluza-Klein excitations, you will have several kicks of the spectrum that could, in principle, probe an extra dimension. Of course, Catherine doesn't have now. Before it didn't have the sensibility to probe this, but the update of the experiment, and in particular, I think Ptolemy, which will have much more sensitivity, it can, could probe it.
I encourage you to ask questions. You can always learn something. Yes.
Can you please go to the CNV?
Yes.
Power spectrum?
Here you want?
Yes. So, observationally, how much better do the error bars need to get before we can?
Oh, in this region, you
in that
mean?
region, yes.
I mean, you can see from here.
No, I know, but
Yeah.
is it? What is
I mean,
the least amount
of course, there is also an ambiguity here because we don't know exactly where the transition will happen. I mean, if it happens more at larger distances, then of course, because at some point here you cannot improve. There are always errors because of the what is called the fact that we have only one universe. We cannot have much statistics. But in the region around here, in principle, one could start seeing deviations. And in that paper already there are some claims here. There was already some claims that there is already some preliminary evidence for violation of scale invariance, but
Finite size of it.
yeah.
Small L. Yeah.
Thank you.
The scale invariance, of course, is what is called asymptotic.
As-
So there is a range of k from k minimum to k maximum.
Yes, exactly.
That's not really exact scale invariance. This is what is called infrared cutoff and ultraviolet cutoff.
And
So
actually-
you always have an interval. The question is, can you probe the end of the interval? Then you see something.
that this interval is about 3 orders of magnitude only.
Yeah.
So that's the only region. Yeah.
Yeah. The logarithmic scale is just 3.
Mhm.
Differ by a factor of 10 to 3. Yeah. More questions? Otherwise, I will ask you one question about primordial black holes.
Mhm.
Yeah.
You have.
I was also going to ask about
Yeah, please
primordial
go.
black holes. So I just want to understand when you say that they are dark matter candidate. So are we assuming that the dark matter is localized in the universe, or is it that they are fraction of the dark matter? And for example, we are doing experiments on Earth, right, to detect dark matter. So those are different kind of candidates.
Already in 4 dimensions, one could be a possibility that the dark matter is just composed from primordial black holes. Of course, this primordial black holes has to be produced at some point, so we must have a model in which the, for instance, towards the end of inflation, there is a spike in the power spectrum, so that primordial black holes are produced. Here I just said that I didn't mention about the mechanism because essentially here you have a 5-dimensional inflation, which means there is a 5-dimensional inflator with a potential instead of a 4-dimensional one. I didn't mention how you can produce by similar way, but what I said is that if there is a mechanism that produces 5-dimensional black holes, then these 5-dimensional black holes are less constrained from evaporation because they live longer, and therefore you can extend the region of their masses.
Could you please elaborate what you mean by Hawking radiation? This is
Yes,
what you mean,
by Hawking radiation.
So you assume that this thing
Yeah,
is
yeah,
okay.
assume that Hawking
The
radiation.
usual thing is
Yeah.
10 to 15, 10 to 16 grams,
Yes.
because the decay time of such a black hole is just the age of the universe.
Yes.
Okay? So anything which is shorter, you will not see it. So mean evaporation. Right? But anyway, it's very interesting that you can explain. There are models in which you can explain all dark matter by primordial black holes. In many different models. It's a possibility. But there are other things coming from primordial black holes. Yeah. Any more questions? Oh yes, please.
In your model of like micron size dark matter, do you assume that they're magnetized, they have magnetic fields, and if they are?
No. That's
Ah.
this is an extra information. That,
More questions? I have a comment. Professor Antoniadis, as you can see, is an extremely modest person. In fact, it was him and Marios Kiros who proposed in 1990 the whole idea of this large extra dimensions which modify the gravity, on the scales, which people later measured. But of course, the original idea in the first paper needs some time when you have other guys running, So you have what is called Johnny's came lately. Okay, more? No more? Let's thank the speaker.